questions, just throw them right into chat, and then we'll take a look at it. So what I'm going to do here is I'm going to take a look at some of these practice exam problems from exam number 2 for the class. I won't put anything up on screen, but what I will do is I'll write a summary of the question on the board with a little diagram, and then we'll go through it. So let's take a look at this problem here. This is problem 1. Okay, so all the topics here are going to encompass anything ranging from forces, forces in circular motion to work and energy, and we'll go through all these. So number 1 says, Bill and Ben pull a raft through a lock of a canal. Bill pulls with a force of 130 newtons at an angle of 34 degrees relative to the forward direction of the raft. Ben, on the opposite side of the lock, pulls at an angle of 45 degrees, as shown in the picture. So, diagram, we have, let's draw like a little canal here. So this is almost like a river of some sort, and then there's a boat in the middle of it. I'm going to represent the boat as just a single point. And then I'm going to draw the forces that are acting in the boat based on the context of the question. So it says that there are 2 people who pull the raft. So we have at least 2 forces that can be drawn in this diagram. Okay. So force provided by Bill, so I'll call that force Bill, is 130 newtons. Okay. And we have that amount of force, and it's in a direction which is 34 degrees compared to the forward direction of the raft. So whatever you want to define as the forward direction that's being pulled, so let's say you draw it being pulled to the left, or you draw it being pulled to the right, it doesn't really matter. Call that the forward direction. So let's say I make this forward direction, let's actually draw it a little bit more to the left so that we can draw the forces going to the right. So this line right here, this could be like the x-axis, and that's going to be my forward direction. This is like the positive x. And then my force will be going in a direction which is off the axis. Let's say this direction, call that force Bill. And then there's an angle in here. Let's call this angle theta 1 for the time being. And let's say that theta 1 is an angle given. That angle is 34 degrees. So that's the information for Bill. Now, we also have another person named Ben. He's on the opposite side of that and pulls at an angle of 45 degrees. So compared to the same forward direction, we're going to put a force which is 45 degrees off this axis, but it's in the other direction. So it's going to be below the axis in this diagram. So like this. Okay. Call that force Ben. Force Ben. I don't think we are given the force for Ben. It says in part A of this question, what force F should Ben pull so that the net force, or in other words, the total force, in the of the 2 directions, so net force of the 2 crewmen is in the forward direction to the left in the picture. Now, in this diagram that was originally drawn, the forces, I think, were aimed more to the left. It doesn't really matter. You can just draw them the other way so that they can be to the right as well. What we want out of this is the net force of these 2 being perfectly along this line. So we know we want it to be along that line because it says we want the net force of the 2 crewmen in the forward direction. So what's going to happen is each of these forces here have a component, x and y. So, for instance, the force from Bill will pull to the right, but it's also kind of pulling upward in this diagram. The force from Ben is also pulling to the right, but kind of down. So this force from Bill kind of going up and the force from Ben going down are going to tend to subtract from each other or tend to cancel each other out. So the question is, what's needed to make them cancel out? So what is the force provided by Ben? Given that the angle, let's call it theta 2 below the axis, that angle 2 is 45 degrees. Now, we want the total force to add to 0, so when we want to talk about the total force, we're talking about adding things together. So we use the sum of all forces. So the sum of all forces, since we want to talk about forces in different directions, we have to split them into components. So we have to talk about, do we want to do this in the x or do we want to do this in the y? What we need for this to cancel out to be along the axis is for the y components to cancel, because we know the x components are both to the right and just continue adding to the right, but we need the y components to cancel, so we probably should be looking at the y direction. So the sum of all forces in the y direction equals, we could just say it's equal to 0, or if you want to write out Newton's law in full first, that might be a good idea. So mass times acceleration in the y. At this point, we could just say that the right side is 0 by saying there's no total or net acceleration in the y direction. This object will not accelerate up or down in this picture, only motion along to the right. So we're going to say no acceleration in the y, motion only along x. So now, the right side is going to be 0, so we're just going to write right side 0. The left side, we're going to add up all forces, and we're going to account for the direction as well. So we have forces in the y. There are 2 forces with a y component that we could draw. So for instance, I could take this force from Bill, and I could draw it down to the axis like this. Make it perpendicular to the x-axis, so that gives me my y component. And I could do the same thing with force from Ben too, like this. Okay, so I have 2 separate force triangles. Now, to get the y components of them, I need to focus on only one part of the triangle. Remember that the force vector is the magnitude or the hypotenuse of that triangle. So to get only one of the legs of the triangle, I need to use a trig function to relate it to the angles that are given in the problem. So for instance, if I were to draw, let's say, the force from Bill, just that triangle off to the side, I would say, okay, so I have the force from Bill, diagonal, and then I would have its x and y components here, like that. So what we would say is, based on this angle, theta 1 here, and I want to relate it to each of these sides. So let's say we do the y component. The y component here is the opposite side of theta 1. So if it's the opposite, and I want to relate it to the hypotenuse, then I would say that if this is force Bill y component, then the trig function that relates those together would be the sine of that angle. So sine of theta equals force Bill, y component, divided by force Bill. Since I want to write in the y component into my sum of forces, I'm going to solve for the y component. So if we just move this over to the left side, we get force Bill sine theta equals force Bill y component. I can do the same exact thing for the bottom triangle. It's going to be basically the same triangle but flipped, just with different numbers. So the y component on the bottom triangle uses the same trig function for the same reason. So from that bottom triangle, you could also say, by the same reasoning, that if you want the y component, it would be force, in this case, it would be Ben, sine theta equals force Ben y component. Okay. So we get the y components of both Ben and Bill, and that's what we're going to put into the sum of all forces. But now we also have to pay attention to the direction too. Notice that if you were to draw in, let's say, the y-axis, so if you treat your mass or object as the center of the coordinate system, then you can draw your coordinate system off of that. So I already drew the x-axis horizontally in this picture. This will be my vertical axis, the y-axis, with positive y going up. So that means that the force from Bill is in the positive y direction for its y component, and force from Ben is in the negative y direction. So how I express this is by writing my force y components. So let's start with a positive one, so that'd be force Bill. I'll write this one out first, so force Bill sine theta, and that is positive, but then the y component of force Ben is in the negative direction, so what I'm going to do is I'm going to write minus. So force Ben sine theta, and then equal to 0. So we have the forces all listed out. They're equal to 0. They add to 0, but in this case they subtract because they're in opposite directions. I want to solve for the force from Ben in this problem. So I'm going to try to get force from Ben, only this part by itself. So what I'm going to do is I'm going to add this whole term over to the right side. So I get that left side we have left over force Bill sine theta. This term gets moved over to the right side, so it's equal to force Ben sine theta. Also careful with the subscripting, because if you forget the subscripts, it makes it look like they're going to be the same angle. It's actually theta 1 and theta 2. Okay. Two different angles. Now we can take the sine of angle 2, and we can divide it over to the left side to get force Ben by itself. So we have force Bill sine theta 1 divided by sine of theta 2 equals the force from Ben. We're going to go through and make sure that we have everything. So we have force from Bill. That's good. That's provided. We have both angles, theta 1 and theta 2. So all we're going to do here at this point is we're just going to calculate that. Okay. Now, we could also still figure out a reasonable estimate for the answer, because notice that if these forces are supposed to cancel out, notice that because of the different angles they're pulling at, then the y components and the x components have a different ratio. So the thing is that for theta 2 being bigger, that means that this force right here is going to have a bigger x component, it's a bigger y component to x component ratio. What's going to happen is with that bigger angle, you're going to find that there needs to be less force. Actually, I think it's more force from Ben. Yeah, there needs to be, I think it's because if it's 34 and 45, they're not that much different, so you should get an answer around 130. If your answer's too far from 130, then let's say if it's like more than 200 or like less than 100 or so, you're probably not on the right track. So let's expect something around 130-ish, let's say. So let's calculate this. Now, we have force from Bill, which is 130, times sine of theta 1, which is 34 degrees, divided by sine of 45. Okay. So for this one, we get that it's 102. So force from Ben equals 102 newtons. Now, we expected this answer to be a little bit different, but not too much different. It's within a reasonable range. Is there any questions on this part of the problem? And what I'll do here is I'm just going to number some of these things, and then if you have a question at a specific point, you can point me to whichever number, like a line number that I'm using. So for instance, the diagram is 1, the information here is 2, and so on. Let me know if you have any questions, or give me a thumbs up, and then we'll move on to the next part. I think there's, if you want to do a thumbs up, there's an emoji button right next to the chat, so you can just give me something from there. Okay, so let's take a look at the next question. Okay. So for part B of this question, if the raft has a mass of 14 kilograms, what is the net acceleration of the raft? So it says we may ignore any frictional or resistance forces, and that's pretty much almost every question. It's a way of saying that there's no other forces we need to account for in this diagram that would affect its motion if there's no resistance or friction of any kind. So we have the forces from Ben and Bill now. So it's 130 and it's 102. Okay? They were comparable in size. Now, to get the net, or in other words, the total acceleration of the raft, we need to consider which ways are the object allowed to move along and find the acceleration along those directions. So for instance, in our diagram, we know that in here, from a bird's eye view, we know that this mass could, in theory, move anywhere around here. But in this situation, based on how it's being pulled, remember that the y direction components of these forces cancel out. We don't want this object to be moving at all along the y-axis. So we know that the acceleration along the y, if it's never ever going to move, is going to be 0. But this object is going to still move along the x-axis. Now, just because it's moving, it doesn't mean it's going to accelerate, but it could accelerate. In this case, it should have an acceleration, because if these are the only two forces in this diagram here, we have that these both will have an x component to the right, so they both add together to a bigger x component force to the right, which will cause an acceleration. Let's erase out this part here. So part B. Okay. For part B, what is the net acceleration? So to find the acceleration, now there's a couple ways you could think. Is one, that's a kinematics quantity. If it's a kinematics quantity, you could potentially use kinematics to solve it, but it means you probably need other things like distances, times, speeds, etc. But in this case, we're given forces. So we know that we probably should be relating this acceleration to forces, which is best done with Newton's law. We're going to repeat Newton's law again like we did in the last part, but we're going to instead do it in the x direction, because that's the direction that we expect it to accelerate in. So sum of all forces in the x equals mass times acceleration in the x. I'm first going to ask, on the right side, do we have or expect any acceleration? Well, that's what we're finding, so we're going to leave that side alone. So mass times the x acceleration. Left side, we handle by, again, writing all the forces that have an x component and accounting for the directions. We again have two forces, but we have to ask how many of them have an x component. It doesn't matter if a force points in the y direction here. If something points in the y direction and not in the x direction, we don't count it. It has to have an x component. In this problem, they both have x components, so we do have two forces with an x component. Using the same stuff I did earlier with the trig. So, for instance here, when we did the force from Bill and we drew the triangle out off the diagram here, we didn't touch the x component, but now we need to do that. So if I said, we have force Bill, and then call it the x component, it's going to be the same exact thing that we wrote for the y component, except that we're going to change the trig function we're using. Because we're still using the hypotenuse, because we know that piece of information, and we just want to relate it to, in this case, the adjacent side. So adjacent and hypotenuse now use cosine instead of sine. So we should be able to just use the same exact thing, but just change the sine to a cosine. So I will write that because that force is pointing to the right, which is in my positive x direction, I'm going to write positive force Bill sine, in this case it's theta 1. Now when we write the x component of the force from Ben, it's not going to be negative this time, because it was negative for the y direction because it was going down as opposed to up. For the x direction, it's still going to the right just like the other one, and that's in the positive x direction. So in this case, we're still going to write positive force Ben, and then it's going to be sine of theta 2, and that's equal to the right side. So to reiterate, we're going to add them together because they're both pointing to the right along the positive x direction, and then we're both using sine because, not sine, sorry. Probably think I'm cuckoo. It's cosine. Okay. Both using cosine because they're both the adjacent side along the x-axis. So adjacent and hypotenuse will be cosine. We are solving for the acceleration, so we're going to just simply need to divide off by the mass to solve for that. So we should have that, all the stuff on the left side, force Bill cosine theta 1 plus force Ben cosine theta 2, all divided by the mass, is equal to the acceleration. Okay. Live stream is not working at the moment. Let me know if you can still see the live stream or not. Let me know if everything is good now. make sure we're still good here. Any confirmation from anyone if it's still working? Looks like it's still working on my end. Okay, what I'm going to do is I'm going to continue working through the problem because I think it seems like it's still working, but let me know. Okay, let's erase this. All right, so now, hopefully it's still working. So we're solving for the acceleration, so we just need to divide off by the mass to the other side. We're going to check that we have everything. We have the force from Bill. We have the force from Ben from the previous part. We have both angles. And the mass is given in the problem. Okay. So if we read through here, if the raft has a mass of 14 kilograms, so given that the mass is 14 kilograms, with that, all we're going to do here is we're going to just plug in to all this since we have everything. So the acceleration in the x direction equals force from Bill was provided. Force from Bill was 130 newtons. The angle that it was aimed at was 34. So we do cosine 34. And then we add force from Ben previously found. That was 103 or 104, I believe. I think it was about 103. Times the cosine of, now this one's 45 degrees. And then all divided by 14 kilograms. Still no confirmation if it works or not. Let me know if you can still hear me. Okay, so 103 times cosine 45 plus that term plus 130 times cosine 34. And then all of this divided by 14. Okay, so the acceleration is 12.9 meters per second squared. Awesome. Cool. So we get this acceleration, and we know it's going to be in meters per second squared. Well, it's an acceleration, but the units do work out because you have newtons in the top, plus newtons gives you newtons. Newtons divided by kilograms will give you meters per second squared. Okay, so this looks good. Are there any questions on this part before we move on to the next question? Let me know or give me a thumbs up. And then I'll number these so you can reference to these. 2, let's call this 3, 4, 5, and then 6. Okay. Problem number 2. We used cosine because it's on the x. Yes. Not simply because it's on the x, it's because it's the adjacent side to the angle. The x in this case is the adjacent side to the angle when you draw the triangles. And then y is the opposite side. awesome. Let's carry on then. I'm going to erase this one out. So let's take a look at number 2. So problem number 2 says a mass, which is given 4.52 kilograms, is suspended from a fixed point and with a massless string of length L. The string makes an angle of 17 degrees with the vertical if the mass moves in a horizontal circle with constant tangential speed given as 1.25 meters per second. What must be the length L of the string? Okay. So there's a diagram given for this. Now, even just by reading the problem, you could still figure out what the diagram needs to look like. So just to emphasize here, you have some mass which is suspended from a point with a string. So something is just hanging. Okay. So it would naturally hang vertically. But it says here that the string doesn't hang down vertically, it hangs at a 17-degree angle from the vertical. So instead of hanging straight down like this, it goes like that. Okay. But it says that the mass moves in a horizontal circle. So we're expecting something to do this. Okay. So the picture is that we have a string that's attached to somewhere. Let's write this as the attachment point. There's a string that goes off, we can draw this to the left or the right, it doesn't really matter too much, as long as we draw the vertical line, and given from the problem that the string is in a direction which is some angle away off that vertical line. So the string will support this mass on the end of it. Okay. Now, if you were to just let this go, what would happen is it's basically like a clock or pendulum. It would just swing back and forth, but that back and forth motion would be on a vertical circle because you would see that there'd be like a circle that goes vertically like this, and if it would just swing back and forth, it would be a vertical circle. But it says in the problem that it's traveling in a horizontal circle. So instead of letting it go, what you kind of do is you kind of push it so it basically goes around in this path here. So if we kind of draw that in, there's this horizontal circle that it goes in. And the vertical line would just go straight down. Okay. Notice that it's drawn in such a way that the vertical line goes straight down and intersects with the horizontal circle, so that where it hits that circle, that is the center of the circle. So this is going to be the center of your circle here. Let me just draw this. Okay. Center of circle. Okay. And let's just say that the radius of that circle is r for now. We may not know what it is, but I'm just going to label that distance from the center of the circle out to there as the radius r. Okay. Now, we're given that the angle that this makes with the vertical is 17 degrees. So it's anytime you have like an angle given and they say with respect to this or from this line, in this case it says 17 degrees from the vertical, what you'll want to do is look along the vertical line first and then the angle from that vertical line to, let's say, the string in this case. That's our 17-degree angle in this particular problem. Okay. So I'll write in this angle theta in this triangle. Theta is 17 degrees. Now, the string has a length L. It's not given, so let's just call the string L. The mass is given. The mass at the end of the string is 4.52 kilograms. And it says in here that the mass moves in the horizontal circle with the tangential speed of 1.25 meters per second. So what it's going to do is it's going to continue to move around like this in the circle, and the rate at which it does it, the speed, is 1.25 meters per second. Okay? So v is 1.25 meters per second. It says, what must the length L of the string be? So we're solving for L. So we don't know what L is. Now, there's a couple things that you might want to think about when you're being asked for, in this case, to solve for L. In this particular problem, now, just to start off with, we should immediately recognize before anything else that there is circular motion in this problem. Okay? We have something that's going in a circle. Okay? If it's a circular motion problem, then we should kind of think about things that relate to circular motion, which are relating to, for instance, centripetal force, centripetal acceleration, Newton's law, which relates the two together. Those are some things to think about. And there's also an equation for the centripetal acceleration in a circle as well. So we could talk about a lot of stuff with the circle just as is. But the thing that we're trying to focus on solving in the problem is not something that's in the circle. It's something that's kind of related to the circle, because the string hangs at this angle and it has a length. It stretches out to where the mass is, which is basically going to determine what the radius of that circle is. If this angle were bigger or smaller, what would happen is the radius of that circle would get bigger or smaller. So there has to be a way to relate this length to the circle here. And the way to do that is to realize that there is a right triangle here. Okay? So because this is a vertical line here, the circle is horizontal, so that radius is a horizontal line, so that makes a right angle. And the length is the hypotenuse of that triangle. So if I focus on that part from the side, L, let's call this vertical distance here, let's just call that H. We may not ever use it in the problem, but just in case, let's call it H. And then the radius of the circle goes horizontally like this, and that's R. And this is at a right angle. These things here can be related together, especially because you have this angle here in the upper left-hand corner of the triangle. So the easiest way to relate this would be using the given information. Your two options here would be, one, you could relate all three sides together in a right triangle, and that's using Pythagorean theorem. A squared plus b squared equals c squared. The other way to do this is to use the angle, which is actually the one that's given in the situation. I would probably rather use the angle simply because I have it. Okay? So using this angle here and wanting to find L, I need to use the hypotenuse. But then I said it's related to the circle, which has a radius R. So I know I need to be relating the radius to the length of that string. Radius would be the opposite side of that angle. L is the hypotenuse. That trig function opposite over hypotenuse is the sine. So sine of theta equals opposite, which is R, divided by the hypotenuse, which is L. The goal is to solve for L, so what I'm going to do is I'm going to move L over to the left side by multiplying it. I'm also at the same time going to take the sine of theta, and I'm going to divide it over to the right side. So I'm basically going to swap positions. Okay? So L equals R over sine theta. This is what's going to allow us to find the length L of the string. We need to check if we have everything. We have theta, it's given in the problem. But the radius of the circle, we do not have. So what that means is we need to go find it somewhere else. So now the goal, in order to get L, is to find R. Find R in order to find L. The radius of the circle is going to be circular motion that we want to talk about, because that's where we use the radius. So we want to think anything that's related to circular motion here. Now, we are given the mass and the velocity of it. Okay. So if we know the mass and the velocity of it, we should look for things that have some of those things in it, possibly, that relate to R. So what we can find here is that, okay, we have centripetal acceleration. It talks about the radius and the velocity, so I'll write that as one possibility you could use. Centripetal acceleration, you can either write AC for centripetal, or I like to use a subscript R for radial acceleration. It's the same thing. So radial acceleration is the same thing as centripetal acceleration. Equals v squared over r. So should I use that? Possibly, and it has r in it. It has v, which I do know, but then I don't know what the acceleration is, so maybe not. The other option is to use, let's write over here, the sum of all forces. When you're doing circular motion, it's the sum of all forces along the radial or the radius direction, also written as centripetal, equals mass times acceleration in the radial direction, or centripetal. Okay. So what this means is that we need to, whenever we use this for circular motion, we need to have a diagram for the circle. So what I'm going to do is I'm just going to draw the circle. Okay. This is my top view. Okay. In other words, I'm going to take the whole thing and I'm going to look at it from the top straight down. So what I should see is, because the circle is horizontal, I should be able to see the circle when I'm looking straight down onto it. So this is like the bird's eye view of it. The mass would be somewhere along the path of the circle, and it doesn't really matter where you draw it, because the most important part when you do sum of forces in circular motion is to consider forces that either point towards the center or point away from the center. So when you draw the forces that act on this object, okay, again, keep in mind that this is the bird's eye view, so you're looking down onto it. If we were to draw forces, okay, if we go back to the original diagram where we can see the whole three-dimensional picture, let's say we draw those forces there first, and let's translate it over. On this mass, we would have that, because it has a mass, it should have a weight, or the force of gravity pulling it straight down, okay? Because this diagram is right side up. You'd just be looking at it as you would anything else. So there is a weight acting down on it. Label that weight either W or mg. Now, this mass is not just being pulled down, but it's supported by the string. So when you have a string or a rope or chain, you should have another force which points along that string, rope, or chain, and that's a tension force. So always acting on the mass and away from it along the string. Call that T for tension. Okay. Now, these are the forces that we have acting on it. So notice that this diagram will not just translate over to this diagram right here. Okay. Because we're looking straight down onto it, we're not actually going to see the weight, because when you're looking down, the weight is going in the same direction, so you can't draw that. However, if you look at this, one of these forces does have a component which points toward the center of the circle, which is actually the tension. So if you were to draw any force in this diagram here, there would be one force, and it would point toward the center, and it would be just the component of the tension. So call that tension radial component, TR. In this diagram, where that corresponds to is if you took this force here and you broke it up into a triangle. So if you did this, okay, I'll draw that off to the side here to draw it a little bit bigger. So if I copy this force down here and just draw it a little bit bigger, okay, the tension goes diagonally, and you would break it into a component that goes vertically, like that, and a component that goes horizontally. Okay. So the vertical component would be up and down along the y-axis, but the component we care about is the component which goes along the horizontal. That's in the radial direction of the circle. So the radial component would be like your horizontal component. And the angle in this triangle is not in the bottom, but it's on the top. That's the part to be careful about. So what we need to do is we need to find a way to rewrite the radial component, TR, in terms of things we know. So for instance, the angle theta here. Okay? The angle theta is 17 degrees. Now we could also write it in terms of t as well, but we don't actually know the value for t. But there is another way to get the value of t. So what I'm going to do is I'm going to relate it here first. So I'm going to say that the radial component is the opposite side of that angle. T is the hypotenuse. So opposite and hypotenuse is going to be the sine function. So sine of theta equals opposite, which is the radial component, divided by the hypotenuse, which is the whole tension t. So this means that the radial component of the tension equals t sine theta. So I'm going to take that and I'm going to use it in here. Okay? Whenever you're doing circular motion, anything that points toward the center of the circle, okay, so no matter where it is, up here, left, bottom, anywhere, from any point on the circle, if something points toward the center, it's taken to be positive, and if it's out away from the center of the circle, any direction like this, it's negative. The tension radial component does point toward the center, so it is taken to be positive. So what I'm going to do is when I use Newton's law here, okay, so in Newton's law, I'm going to again start out with the right side. I always ask, do I have acceleration? Now, the thing is, in circular motion, if it is going in a circle and you're talking about the centripetal acceleration, there has to be. So we're going to have that, but what I'm going to do is, so mass times the radial acceleration or the centripetal acceleration, we do have the equation for it, and it puts it in terms of the velocity and the radius. So I will drop that into there, so v squared over r. Okay. On the left side, we need to consider all forces that point toward or away from the center of the circle. In this case, just the tension radial component, which we found to be t sine theta. Okay. So we have positive t sine theta because it points toward the center of the circle. The goal of the problem was to find L. That was the original goal. We needed to find r, so what we're trying to get out of this is the radius r. Notice that if you kind of spot check if you have everything, you do have the mass and its speed. You do have the angle, but the only thing you're missing is the tension. So we have everything except for the tension. So now we need to find the tension. Okay. So to find the tension, now that force points diagonally. Okay, so it goes up in this direction along the string. That means that it doesn't just have a horizontal component, it also has a vertical component too. Call it Ty. If we could find a way to use the other direction, in the y direction, we could possibly find the value of t using the y direction. So what I'm going to do is I'm going to erase part of this. If there are any questions you have up to this point here, let me know, or give me a thumbs up before we keep on moving on to solve this. Okay. Let me number this as well just so you have a reference. So 1, information's 2, this is 3, 4, 5. So let me know, and then we'll carry on. Okay, good. good to go. Okay. Let's keep, we need this part right here, and we need this part right here. Okay, so let's erase out this here. Let's erase this. Let's work off of that. Okay. So we're going to look at the y direction now. So sum of forces in the y equals mass times acceleration in the y. So we're now going to be looking vertically up and down in this picture. Run through the same questions, but this time this is nothing to do with the circle, it's just up and down. Right side, do we have any acceleration? So in other words, we need to consider the motion of this object vertically. So will this object attached to the string ever accelerate up or down? The answer in this case would be no, because the angle is kept constant at 17 degrees. If it's kept constant, all it's going to do is keep on going in that horizontal circle, and it's never going to move up or down in the problem. So we know that there's no motion in the y direction, so we cross out that acceleration. Okay, so no motion in y direction. Okay. Now, the right side is 0. Left side, we account for all forces that have a y component. In this diagram, there is a total of 2 forces, and in this case, we do have both of them with a y component. So the weight points vertically down, so that's along the negative y direction, and we have a tension which doesn't point perfectly vertically, but it points diagonally. That means that there is a component which does go up. So we should have 2 things that we need to write here. So for the tension, what we had was that if we were using this triangle here with T along the hypotenuse, and we broke it into components, okay, this time we care about Ty over here, with the angle again being in the upper corner of the triangle. This time, in order to use Ty, it's the adjacent side to this angle, and we still want to relate it to the hypotenuse, so adjacent and hypotenuse is going to use cosine. So we have that cosine of theta equals adjacent, which is Ty, divided by hypotenuse, which is T. When you solve for Ty is T cosine theta. That's going to be the vertical component, or the y component, of the tension force. Because the weight already points down, the y component is the whole thing, so we just use mg. So how we're going to write this is, first, we're going to write that Ty is in the positive y direction, so we're going to say positive T cosine theta. Okay? That's the first thing. The second thing is the weight pointing down, which means it's negative, so we should write minus mg. This is going to be the use of the y direction, is to get the tension, because we can see the tension is there. And if you look through everything else, you know what the value of g is. It's 9.8 meters per second squared. We know the mass, it's given, and we know the angle, it's also given. So we can find the value of t to then solve for the rest of everything in the problem. So what I'm going to do is I'm going to get t by itself by moving the weight over to the other side, so add it over. It's going to be t cosine theta equals. Add that over, it's positive mg on the right side. I'm going to go back to using this equation later, so I'm going to erase it for now, but we will use this in the end. Okay. So from here, we need to get t by itself, so we're going to divide off by cosine theta to the right side. So t equals mg divided by cosine theta. we do have everything. So we've got the mass, got G, and got theta. We could either just plug it in here and just calculate that tension, or we could drop it into here and continue solving it. What I'll do is I'll break it into different parts and I'll just calculate it. So equals, now actually, but one second. Now the benefit to plugging it in as it is without plugging in any numbers would be is that you might be able to see if anything cancels. If you plug in the numbers now, then you won't get that benefit, even though you will get the tension, which they could ask you in the problem. But let's see what happens if we plug in the tension straight into where we needed it over here. Okay? So we're going to plug in T into this equation for circular motion. So into Newton's law for circular. Okay. So with that, we're going to take this equation here that we found earlier from doing sum of forces in the radial direction for the circle. We're just going to drop it in for T. Okay. So plugging in for T, that's the first thing we write. So it's just going to be mg over cosine theta. So mg over cosine theta. That's now plugged in for T. We have sine theta here equals, right side is mv squared over r. Okay. So mv squared over r. Let's write that down. So that's the Newton's law for circular motion, just plugged in for T. At this point, you could just solve for the radius. There is, however, a couple of things you can do to clean this up to make it look nicer. So for instance, the mass appears in all the terms because there's only one term on the right side and there's only one term on the left side. If something appears in all of the terms on both sides of the equation, then you can cancel it. So for instance, since the mass appears here and here, we can cancel it. So the mass never mattered in the problem. Okay. Yet at the same time, mass does matter. That was bad. Now, solving for the radius. So what we're going to do is we can do one of two things. We could just move everything over and just solve it because we do have everything. If you do want to do this, this is optional in this problem, but it's a good thing to know because some other problems will do this to you. So it's good to have this trick in the bag. Whenever you have sine and cosine here, when you have sine divided by cosine particularly, sine divided by cosine is actually tangent. So you could rewrite this as G, and that part is tangent because it's, again, sine of cosine. So G tangent theta. Okay. So again, optional for this problem. You don't need to do it, but in some problems that's actually a good way to actually solve the problem, is by combining them into one trig function. Equals. Right side, all we have left over is b squared divided by r. Okay. To solve for the radius, we're going to move the radius over to the left side by multiplying it over. So it becomes just r on the left side. We're going to take g tangent theta and we're going to divide that over to the right side. So basically r and g tangent theta, they just swap places. Okay. So r equals b squared over g tangent theta. Okay. We do have everything at this point, so we could find the radius. Or again, if you want to just plug it all in at once, we could plug this into equation for L. Okay, so we wrote something down earlier for the equation of L, and we actually said that it was L equals and that was going to be based on this triangle here earlier. I believe we said it was radius, that's going to be sine. It was sine of the angle, so it was I think it was r over sine theta. Yeah, I think this is correct. Sine theta would have been opposite over hypotenuse. Yes. Okay. So this is what we wrote earlier for the equation for L. We just needed r, so what we're going to do is we're just going to drop this whole thing for r and just drop it into there. Okay. So L equals, so in the top you have v squared over g tangent theta. And then this is all divided by sine theta. Okay. If you want to make this look a little bit cleaner, we can, or we could just drop it in. It doesn't really matter. At this point, I'm just going to drop it in. The speed is given. The speed is 1.25 meters per second. We're going to take that value and we're going to square it. Okay. That's going to be divided by, we have g, which is 9.81 meters per second squared. Tangent of the angle, which is given, 17 degrees. And this is all over the sine of the same angle, which is 17 degrees. We're just going to calculate this out here. So we have 0.81 tangent 17 and sine 17. It's all on the bottom, and then in the top we have 1.25, and don't forget to square it. Forgetting to square is one of the most common calculation errors. 1.78 is what we get for that. So the length of the string is 1.78. We are expecting it to be in meters, but let's confirm that we do get meters out of this. Notice that the only things with units here are in the top with the velocity and in the value of g. So we have meters squared over second squared divided by only meters over second squared, so we should get meters from canceling that out. 2, label that 3, 4, 6, 8, 9, 10. Okay. Let me know if there are any questions on this. Point me out to any number if you have any questions. Otherwise, just give me a thumbs up and we'll move on. This was also probably the longest problem out of all of them. This was probably the longest and most complicated one, just for reference. Let's see, what's the next question? Awesome, thumbs up. Cool. Hello, by the way. Question number 2. Finish question number 2. Let's go to question number 3. Okay. Okay. So for number 3, and we got no questions, we're good. Okay. I'm going to erase, let's start from the left half here. Okay. So for number 3, this one says, Stacy weighs herself in the bathroom and measures her weight to be 625 newtons. Okay. I'm going to make a note on that in a second here. In an elevator, her apparent weight, quote unquote, is 708 newtons. What are the magnitude and direction of the elevator's acceleration? All right. So for this problem, we need to talk about the idea of apparent weight versus your true weight. Okay, so in this problem, it says that the weight, if you want to call it W or mg, the weight is a given value and it's 625 newtons. Okay. So this is problem 3. Okay. The weight, again, is not the mass. The mass times the acceleration of gravity is going to give you the weight, which should be a force in newtons. So mass is in kilograms, weight is in newtons. So we know it's going to be the weight of 625 newtons. The apparent weight is 708. So versus apparent weight, quote unquote, is 708 newtons. Okay. So what's the difference between these? So the difference comes from what you feel when you're in the elevator in this problem. So if we draw out this elevator, and let's just say there's a mass here. Okay, there's a person standing, but I'm going to represent them as a mass, as a point mass. If we were to draw the forces that act on them, okay, so for instance, they have a mass, therefore they have a weight going straight down, weight mg. Now, they are standing in an elevator, which means they're standing on a surface. They push into the surface is going to prevent them from going through, so it's going to push back. That's the normal force, only occurring when you're on or in contact with a surface. Let's call that normal force lowercase n. Now, from here, so the elevator is also accelerating. We know that the elevator is going to be moving up or down in the problem and accelerating. So what's going to happen is these two forces are not necessarily equal and opposite. They kind of look like they are, but nothing says in this problem that they have to cancel out and add to 0, because if this object is to accelerate up or down, then the size of one of these forces has to be bigger or smaller than the other one. So that gives the idea of apparent weight, which is what you feel when you're in the elevator. So if, for instance, you're going from the second floor down to the first floor and the elevator starts moving down from rest, you feel like you're a little bit weightless. So your apparent weight is less. If the elevator goes from the first floor to the second floor and starts moving up, you'll start to feel a little bit heavier, so your apparent weight is larger. So how do you find the apparent weight? So turns out it's actually just the normal force in this problem. Think of it as if you were standing on a scale in the bottom of the elevator. What would happen is the scale would read something larger or smaller, and the reading of it is actually just going to read what the normal force is, because when you're standing on a scale, how much you push into the scale is what it reads. But the normal force is a measure of how much you're actually pushing into the surface. If you push into the surface with a certain amount, it pushes back with a certain amount. So the normal force is actually just going to be your apparent weight. Okay. So this is a way of saying that the value of n is 708 newtons. Now, in this question, so we have that we want to find the magnitude and the direction of the elevator's acceleration. We know things about the forces because we were talking about the weight and the apparent weight, so those are forces that we're going to be discussing, so the normal force in this case. We have information about forces, and we want to find the acceleration. Naturally, you're just going to say Newton's law, because that's a relation between force and acceleration. So what we're going to do is we're going to define a direction here that we're going to work with. These are vertical, so I'm just going to say that the positive y direction in this picture is upwards. Okay, so Newton's law in the y direction says sum of forces in the y equals mass times acceleration in the y. Okay, so starting with the right side again, do we have acceleration? Well, in this problem we're trying to find it, so we're going to leave the right side alone the way it is. The left side says to add up all forces with the y component. There are two forces in this problem, and they are both along the y-axis, so we have two y components to work with. In this case, in our coordinate system being positive upwards, that means the normal force is positive, so I'll write positive n, and the weight is downwards, which means it's negative mg. So normal force minus the weight. We want to solve for the acceleration in this problem, so I'm going to divide off by the mass and just solve for the acceleration. So it should be this whole left side divided by mass. So we have normal force minus mg, all divided by the mass, is the acceleration in the y direction. So from here, we're going to go through and check that we have everything. Okay. So we have the normal force, that's just the apparent weight. We have, now, we know what the value of g is, but we actually were never given the mass in this problem. Okay? So we don't know what the mass is. But we know something that's close to the mass, which is the weight, and we know that it's just mg. So we could easily find the mass by just taking the mass and then detaching the g off of it, so it would be 625 over the value of g. So what I'm going to say is let's take the equation for the weight, so W equals mg. W equals mg. So that if you solve it for the mass, you can just easily get it. So it's the weight divided by gravity. So the weight is 625 newtons divided by the value of g, which is 9.8 meters per second squared. Let's calculate that real quick. So 625 divided by 9.8. 63.8 is what we get. 63.8 newtons divided by meters per second squared will only leave you with kilograms. That is a mass. We're going to take that 63.8 kilograms and we're going to plug it in to there. So the acceleration in the y equals the normal force, or the apparent weight, which is 708 newtons, minus mg, so m. So now actually you can do something a little bit different here. You're still going to have to plug in the mass into the bottom because it's by itself. That's why we needed the 63.8 kilograms. But because the mg is lumped together in the top as one piece, that's just the weight. Okay, so we could just write mg as the weight, which we know is 625. So we don't even need to bother plugging in the mass in the top. So 625 newtons. In the bottom, we will plug in the mass because it's by itself. So it's 63.8 kilograms. Let's just calculate this out and we'll get the acceleration. Okay. Now, before we get the value, here's a little conceptual check, is that their apparent weight is larger than their true weight. So what happens is when they're in the elevator, they feel heavier. That tends to happen when you're accelerating upwards. Like for instance, when you're going from first floor to second floor, elevator moves up and you feel heavier. So we're expecting the acceleration to go up in the positive direction. We're expecting a positive value for this. Okay. So 625 and 708, the difference is 83 divided by the mass is 63.8. Okay. We get 1.3 for this. Okay. So equals 1.30 meters per second squared. Okay? A Newton divided by a kilogram will give you a meter per second squared, which is acceleration. Okay? And this answer is positive when you calculate it, so we get the acceleration is upwards, which we expected. Okay? So I should write parenthetically here it's upward. That's the direction of it, and the 1.30 is at least the magnitude. Let's number these, and if you have any questions, let me know, and we'll go from there. So let's label this. These ideas are 1, diagram is 2, equation is 3, 4, 5, 6, 7. So yeah, let me know or give me a thumbs up, and we'll keep on going to the next problems. Question. You said, why is there acceleration in the y? Because the elevator is, so the problem says to solve for the acceleration of it. So we know we need it. But there is acceleration in the y, possibly because there is motion in the y direction. So the elevator and the person is moving up or down in the problem. But even that alone isn't able to tell if there is acceleration, because you could be moving with constant velocity, moving in the same direction with the same speed, and there's no acceleration in that case. But you know there is going to be acceleration in this problem because the sum of all forces do not add up to 0. You have the normal force upward, and you have the weight downward. So with that, given that you know the normal force is the apparent weight in this problem of 708, and you know the weight downwards is 625, you know they're not going to cancel out. So you do expect that there is acceleration along that y-axis in this problem. So that's just from telling from the forces, but otherwise they just ask for it. Let me know if that's good, or if there are any more questions on this problem before we move on to the next one. Awesome, we're all good? Okay. Let's keep going. So on to problem number 4. I think this, oh, does it have another part? No. Okay, so this problem is done. This is a shorter one. Okay. So number 4. In order to push a cart, Boris pushes the cart with a force of 18.2 newtons. If he pushes at an angle of 52.1 degrees above the horizontal, how much work is required to push the cart 1.95 meters? Okay. So they're asking for something relating to the work. So we should think about work concepts. Work, by definition, is, so conceptually, it's the ability of a force to influence the motion of the object. So, but numerically, you would say, okay, it uses force. I would use force to calculate it, and it has to do with moving a distance. So we need to draw out the forces that are acting on the object to discuss what the work done is. So what we're going to do is we're going to draw this horizontal surface, because it's stated that they're pushing something along a horizontal surface. So they push the cart with a force of 18.2 newtons. So if they're pushing the cart physically, let's call that an applied force. Okay, the force applied is 18.2 newtons. And then in a direction of, let's call it theta equals 52.1 degrees above horizontal. Okay. So we're given how much force is applied by the person, and we're given what direction they apply it, in this case above the horizontal as opposed to below it. How much work is done to push the cart 1.95 meters? Okay. So if I represent the cart as a single point in this diagram, here. Okay. We draw all the forces on it because we're interested in finding the work done. So because it has a mass, it immediately has a weight going straight down. The cart sits on a surface, so if it's in contact and pushes with a surface, then the surface pushes back, and that's the normal force, always perpendicular to the surface. In this case, it's up. And let's assume that the cart is being pushed to the right. If that's the case, then the force applied is above the horizontal, so look to the right horizontally, but go at an angle above it. Call this force applied. And the angle theta in here, above the horizontal. Now, it does say to calculate the work required to push the cart. So the work required to push the cart is the work done by that particular force that is pushing the cart. Okay? Or they could rephrase it as what's the force, or what's the work done by the applied force, or what's the work done by that person. So we also are given that the distance, let's call this distance d. The distance d is 1.95 meters. Okay. So the work done, work W equals force times distance, call it d, times cosine of some angle. Let's call that angle phi. I'm going to use a different Greek letter for that than theta, just to make sure what this angle needs to be. Okay. So this is the equation for the work done. The angle in this equation is not always the angle given in the problem. The angle's definition, call it phi, the definition of this angle is the angle between the direction of the force in question. So in this case, we're finding the force, or finding the work done by the applied force. So that means we would use the applied force. But whatever the force we're questioning is. And direction of motion. Okay. The direction of motion would be, for instance, the direction that you end up moving in with this distance of 1.95 meters. So for instance, in this problem, you would move to the right this distance d. Okay. So then you would say, what's the angle between the direction they move, which is to the right, and the direction of the applied force? In this particular problem, notice that if you put the direction of the movement, which is to the right, and you put the direction of the force, which is here at an angle, the angle between the two directions actually is the angle theta, which is given in the problem. So in this case, it is the 52.1 degrees, but depending on the question, it could be a different answer. So if we plug this in, okay, work is equal to the magnitude of the force in question, which is the applied force of 18.2 newtons, times the distance d that would move it. We said it was 1.95 meters. And the cosine of that angle between those two directions, which is in this case 52.1 degrees. Okay. We can just calculate this. A newton times a meter can be rewritten more compactly as what we call a joule, which is the unit for work or energy. Well, 18.2 times 1.95 times cosine 52.1 gives us 21.8. So the work done is 21.8 and more compactly written in joules. This problem was pretty straightforward. I will make a side note to reiterate on this angle. If you were to, for instance, ask for the work done by gravity or the work done by, let's say, the weight in this question, because there's other forces here. I could have asked for what's the work done by a different force rather than the work done by the applied force. Notice that, for instance, because the weight points downwards, if I were to ask for the work done by that force, I would instead use mg instead of my applied force, so I would plug in mg. I would use the same distance, but the angle would not be 52.1 degrees. Remember, if you were to find the work done by a different force, you have to consider its direction. So if it were the work done by the weight, that would point downwards while the motion is to the right. That angle between those would have been 90. So if you were to calculate that in theory, for the work done, you would use an angle of 90 in the equation rather than another angle like 52.1. So make sure you always ask what's the work that you're calculating for which force, and then use that direction for that force, and then use the angle between that direction and the direction of motion. If there are any questions with any of this, let me know, or give me a thumbs up and we'll move on. Okay. You're good? Okay. All right, now, if we're good, let's move on to number 5. Okay. So this one was problem number 4 that we just did with the work done. So number 5. This one says Alice slides down a rough playground slide with an acceleration given. It's 2.81 meters per second squared. Okay. So draw a diagram showing the forces acting on Alice. So we have the slide. Okay. So for problem 5. The slide is implied to be diagonal, so we're going to draw a diagonal down to the right. Okay, so part A, draw a diagram. Okay. So we have this diagonal that represents the slide. Now, we do want to draw some of the forces acting on it, so what we're going to do is we're going to put the mass somewhere along the slide. It doesn't really matter where, but we want to put it somewhere that we can just draw the forces that are acting on it. So from here, we have that it's a quote-unquote rough slide. Okay, so the term rough, so when we're saying that it's rough, okay, that's rough, buddy. So rough translates to it has friction. Okay, so has friction. Now, when we draw the forces, let's draw the more immediate and obvious ones. So because there's a mass here, we're going to say that it has a weight. So there is weight that acts straight downwards. mg, always downwards. The object is in contact with the surface and pushing into it. So that means there is a force pushing back from the surface, which is the normal force. That force is always perpendicular to the surface. So the surface is slanted, so the perpendicular direction is, in this case, diagonally up to the right. Okay? Notice that it's perpendicular. Now, it also has friction, so as the person is sliding down, what's going to happen is there's a friction force which resists what they're trying to do. So what you want to say is which way do they tend to move, and then point the friction in the opposite direction of the direction they tend to move in. In this case, they tend to move along and down the slide, so down to the right, so the friction points up to the left along the slide. So in this case, draw friction like this. Call that lowercase f. Remember that there are two kinds of friction, static and kinetic. Okay. I'm going to leave a subscript off for now. It's either going to be S for static or K for kinetic, but we will add it based on the context of the problem. Otherwise, it's just generally friction resisting its motion. Okay. So from here, we have the free body diagram of this. Now, I could actually add in the angle into this as well. So for instance, I could make this slide into a whole triangle like this. Okay, make it a right triangle so it has a vertical component and a horizontal component to the slide. There's an angle theta in the corner of it. Okay. Now, for part B, we need to calculate the equations representing the components of the forces acting on the person that goes down the slide named Alice. Okay. So for this, we are given that the acceleration A, so given acceleration is 2.81 meters per second squared. Okay. So if we need to calculate the equations representing the components of the forces acting on Alice, then we need to write out Newton's laws, ultimately what it says. Okay, so for part B, we need to do sum of forces in the x direction equals mass times acceleration in the x direction. And we're also going to do that in the y direction too. The problem does not specify doing it in any particular case, one or the other. It just says to calculate the equations, plural, as opposed to singular. So what we need to do is we need to work them both out. Okay? Based on the context of the problem, because we do have an acceleration down the slide, we expect the person to be accelerating along the diagonal. Okay? So if they're accelerating along the diagonal, then what we need to do is consider that it's motion along one single axis. So what we can do is we can make the x-axis along the direction of motion by putting positive x in the direction that we think we're going to be moving in the problem. So positive x is diagonal along the slide. Positive y is just going to be perpendicular to that, so in the same direction as the normal force. So that's my positive y direction. Okay. So when I do the x and the y component here, I should just reference to this axis here. Now, if we do this, so let's do the y direction first. Okay. The y direction, remember, because it's a tilted axis, it's not vertically up and down, it's tilted. What I'm going to do is I'm going to draw the coordinate system on the mass. I'm going to take this and I'm going to just move it onto the mass to better see what has what component. So perpendicular to the slide along this direction is the y-axis, and along the slide itself is the x direction. Okay? So that's my coordinate system. If I'm going to do, let's say, sum of forces in the y direction, okay, so what we need to do is we need to ask, is this object going to be doing anything along this y-axis, which is tilted? The answer is no. The object will never go off the slide and the object will never sink into the slide, so there was no motion at all in the y direction ever in this problem. That means it has no acceleration in the y direction. So we can take this and cross it out and say no motion expected in y direction. Okay. So the right side of that equals 0. on the left side, we're going to write out all the forces which have a y component. Okay. There are a total of 3 forces in the problem altogether, x or y component. Normal force, friction, and the weight. However, we need to ask which ones have a y component. There's only 2 of them out of those 3 that have a y component. First, the normal force, it points directly along the y-axis, so that obviously has a y component. But the weight, even though it points down, not along the y-axis perfectly, it does have a component which goes along that axis. So that has a y component. The friction's along the x-axis perfectly, so it only has an x component and no y component. So what we need to do is list out these 2 forces that have a y component, and we need to write what their components are. The normal force is already along the axis, so that's fine as it is. This force, the weight, doesn't point along the axis, so we need to break it up into components which go along the axis and perpendicular to that axis. So the way we do that, I would suggest going from the mass along the y-axis until you reach a particular point on that axis where if you were to go parallel to the x-axis, like this, if you were to go parallel from this point to the x-axis to where the vector is, like that, so you kind of get this diagonal component here, that would be your x component, and this one would be your y component. Okay? So I'm going to draw this triangle off to the side. However, I will note that if you do a little bit of geometry here by using this angle in the corner here, theta, you move it over to here, these angles add to 90, and then you move it over here and these angles add to 90. This angle in here will be also theta by geometry. Okay. Drawing that a little bit bigger off to the side just so we can break things down easier, we have the weight going straight down, that's mg, and then the components going diagonally. So the y component along the y-axis, and the x component parallel to the x-axis. Okay. So if we have the angle theta in the top corner of this triangle, we can get the y and the x components in terms of the hypotenuse by using the trig function. So for instance, this side here, the y component, is the side next to the angle, so it's the adjacent side. We have adjacent and hypotenuse. So we know we need to use cosine to do that. So for this, it's just going to end up being mg cosine theta. For this side over here, we're going to get that it's mg sine theta because it's the side opposite to the angle. In this particular part of the problem, we're going to write out the y component. So we're going to use mg cosine theta. But one important thing to note here is that if you look at the diagram that we originally drew, the y component goes down along the negative y direction. So it's going to be negative when we write it. So we have normal force in the positive y direction, so we're going to write positive n. And then we're going to write the component of the weight that's along the y-axis, which is in the negative y, so it's mg cosine theta negative. Okay. With this, you would get, if you wanted to solve this around, you would get that the normal force equals mg cosine theta. Okay. So this will give you all the stuff in the y direction. Now, the problem is still relatively vague. It just again says to calculate the equations representing the components of the forces acting on Alice. These are the equations that would account for the components of the forces acting on them. So calculation, it's implying that we're going to have to calculate this out. So what I'll do is I'll plug in the numerical value for this. Now, the thing is they don't give a mass in this problem. So they don't give you a mass or a weight. So the thing is that you can't physically get a number for this in this particular problem. So if you're asked to get a numerical value for the normal force, it's not going to happen. This is the most that you could take it. Okay? That's all you can do in the y direction. Now, if you do the x direction, which we also need to do in the problem, we may end up using this normal force at some point to do something. So over here in the x direction, okay, first thing we ask is, do we have any acceleration along the x-axis? And the answer would be yes. It's also given directly in the problem. They are accelerating, and we know it's along the x-axis. So we're going to leave the right side alone because we have acceleration. Okay. Now, the left side, we need to add up all forces with the next component. We look at our diagram, we have a total of 3 forces, but not all 3 forces have an x component. So we're going to say not the normal force because that's on the y-axis, so it's just going to be friction because that's perfectly along the x-axis, and only a component of the weight because it has an x component. So we should have 2 terms. I'm going to write the friction because I don't need to break it up, so I'll just write negative friction because it points in the negative x direction. It's up the incline as opposed to down the incline. So negative friction. They are accelerating, so they're going to be moving along the slide, so it should be kinetic friction. So minus Fk. Now, the component of the weight we care about, which is the x component, it's the side that's opposite to the angle, which is mg sine theta. So we're going to write mg sine theta, but being careful, it is going to be positive and not negative, because what makes the x component positive or negative is if you are to the right or to the left of the y-axis. So being to the right of this axis makes it positive in the x direction, and this makes it negative in the other direction. So because the x component goes to the right of this axis, it's in the positive x territory. So we should know that it's plus mg sine theta. Most common mistake there is to actually use minus because you think it points down, but down is not a good description for if it's positive or negative x. Okay. So from here, what we can do is we can try to calculate out some of this stuff. We need to expand some of this first. So for instance, there is an equation for the friction that you could expand out. So the most you could do with this, for instance, is use the fact that friction, Fk, equals the coefficient, mu k, times the normal force. I'm going to plug this in for the friction, so we're going to get minus mu k normal force plus mg sine theta equals mass times acceleration in the x. Okay, so rewriting it but just plugging in for the friction. Okay, so that's just this stuff right here. From here, you do technically have the value for the normal force not calculate out, but you have it solved. So you can take the normal force from the y direction and you can plug it into the normal force in the x direction components. So minus mu k, and then plugging in the normal force. So let me colorize this. This is red. Let's plug it in, write it in red. So mg cosine theta. Plus mg sine theta equals mass times acceleration of the x. Now, the problem now, it doesn't say to solve for anything in particular. Again, it's very vague and it just says to calculate the equations representing the components of the force. So with all the stuff that we're given, we can't really solve for any particular thing and do much with it. If I were to solve this problem out for something that I could get, I would realize that, number one, the mass is in every term, so I could just cancel out the mass. So the mass doesn't really matter in the problem. We do have the acceleration. It's given as 2.81 meters per second squared. The angle would not be given in this problem, apparently, so it doesn't give you the angle. You know the value of g. angle appears here, you don't know it, you don't know the value of g, and in this problem you also don't know the coefficient of friction. This is the most that you could take this one out before needing more information to do it. So if you were to just write out Newton's laws, this is what you're going to get by writing out Newton's laws and then plugging in for all the forces and their components. Okay? This problem would need to probably give you the angle or the coefficient of friction or both to do anything more with the problem. Okay? There is, however, another part to this problem. Now, so this next part of the problem actually is going to directly address this issue that we're having. So I believe this is all the problem wants us to do for now, but in part C, this is where it fills in the gap. In part C, it says to find the coefficient of kinetic friction. That's one of the things I told you that was missing. Between Alice and the slide, if the slide is inclined at an angle of 27.5 degrees above the horizontal. That's the other piece of information that we needed, was the angle, and now it's given. So, in this part of the problem, it basically is a way of saying, find this missing thing given the other thing that we were missing. So we now have enough information to solve it. So let's say at this point, we're given theta equals 27.5 degrees. Find the coefficient of kinetic friction, mu k. Okay? So this is part C. That was part B, and that's part A. Okay? Diagram 1, 2, 3. Actually, let me do that. 2, 3, 4, and then 5, 6, and then 7. Okay. So our job is to now isolate the coefficient of friction by itself. Okay, so we're going to need to move everything over to the other side. So first of all, let's move this term, mg sine theta, over to the right side. It's plus, so we're going to subtract it over. So we have left side is minus mu k mg cosine theta. This term is now moved over to the other side, so equals right side. We have mass times acceleration in the x. We subtracted that term, so minus mg sine theta. At this point, we can isolate the coefficient of friction by dividing off, we have a negative sign, and dividing off mg and cosine theta. I will clean it up a little bit before I move things over. The mass is common to every term, so let's just get rid of it. So the mass will disappear from all terms. And let's just divide over the remaining things. So the coefficient of friction is the right side, what we have left over. So acceleration x minus g sine theta. The masses were already gone at this point. So that's the right side, and we're going to divide over the stuff that we want to move over from the left side. So all divided by negative. We have g cosine theta. That's it. This is now solved, so we're going to do a couple of things. We're going to check the units because we've done a bit of algebra, and we want to make sure that it's solved properly. So that can be done by a unit check, and that will mostly assure that you've done reasonable things. The other thing is we're going to expect a reasonable answer because, for instance, it's a coefficient of friction. Coefficients of friction are usually going to be less than a value of 1. It's going to be 0 point something. They can be a little bit larger than 1 on a very rare occasion, but we're going to expect something around or less than 1. So let's check two things. If we plug into here, so what I'm going to do is I'll use this last bit of space in the left corner here to calculate. Let's plug in everything and let's check the units. So mu k equals, acceleration is 2.81 meters per second squared. Okay? That acceleration is down the slide, so it would be positive. If the acceleration was in the opposite direction, it would be negative. Minus g, which is 9.8 meters per second squared, times sine of a given angle, which is 27.5 degrees. This is all divided by negative g is 9.8 meters per second squared times the cosine of 27.5 degrees. So we're just going to calculate this all out. Notice the only units you have in the top are meters per second squared, and you're subtracting that from another meters per second squared, so you do get units of acceleration in the top. The bottom, you only have meters per second squared, so again, acceleration over acceleration. Those units will cancel completely, leaving you with no units, and the units of the coefficient of friction, there's no units. Okay? So that checks out. Now let's check if the answer is reasonable numerically. Calculating this, we have 2.81 minus that, so 9.8 sine 27.5 plus 2.81. Okay, the top is negative. We're going to divide by a negative number. It will give us a positive number, so that's good. And then we have 9.8 cosine 27.5 in the bottom. Okay, this gives us a coefficient of friction of 0.20. This answer is reasonable because it's in the range of coefficients of friction which are realistic. Let me know if you have any questions on any parts of this problem, and either that or give me a thumbs up, and we'll continue to the next one. Where are these problems coming from? These problems are from the practice, or not the practice, the exam number 2 for the physics 100-day class for, I think it was row. So these are all off of exam number 2. Any other questions before we keep on going? So that was 5. Let's take a look at 6. Okay, we are also at about 10 o'clock. Let's go for about another 15 minutes, I would say. I think that should be good. We should be able to get through at least one more in that time. But I think there's a total of only 8 problems on this. So yeah, there's only 9 problems in total. So we will get through most of this. But let's go for about another 15 minutes. Okay. So let's erase this. No more questions. Okay. So problem number 6. Raphael slides toward the baseline in order to hit a winning shot in a tennis match. He slides along the rough ground with an initial speed of 4.75 meters per second. Notice the terms rough ground, that's going to imply friction. if the coefficient of kinetic friction, so now they tell you there's friction, so if the coefficient of kinetic friction between him and the ground is 0.775, how far does he slide before coming to rest? Okay. So, problem 6. Okay. So, the things that were given is, okay, so let's say we have this horizontal ground. It's quote unquote rough, so there is friction. The coefficient of kinetic friction is 0.775. The initial speed, okay, so they're in contact with the ground at some point, okay? This is their initial position. And they move along the ground. Let's say this is the path that they take. They skid along the ground until they reach another point, call it their final position, at which point they come to rest, okay? So at the initial, we know that, so V initial is given as 4.75 meters per second. V final, it was said they come to rest, so 0. With that, we need to find the distance that they slide. It says how far do they go before they come to rest. So we need to find what the distance between the initial and the final point is. That distance is also known as the displacement. So let's call this distance between here and here delta x for the displacement. So we need to know what that is. Okay. Now, this problem has a very kinematics-like feel to it because we're given a lot of information about their motion, what they're doing at any given point. They're going this fast at the initial, and they're going this fast at the final. So both of the velocities are given. We're also trying to find a distance, which is going to be related to those velocities. That's another kinematics quantity. So you could consider taking a kinematics approach to this problem. And based off of the material covered on this particular exam, there was not one topic that was quite covered yet more in depth, which is the conservation of energy, which is the principle you could use to solve the problem a little bit cleaner. Otherwise, it's a kinematics problem. So kinematics, what we need to do is we need to remember kinematics equations. So remember the main ones that we care about are V final equals V initial plus acceleration times time, delta t. V final squared equals V initial squared plus 2a delta x. And the last one that we use a lot is delta x equals V initial delta t plus 1/2 acceleration delta t squared. You could technically work with only 2 of these and you could still solve the problem, but I do find that having 3 is particularly handy, so I will reference to these 3 when doing kinematics. This is all assuming constant acceleration. Okay. The value of the acceleration does not change in the problem, which is most of the time in these problems. So we need to identify what we have and what we don't have. What we're going to do is we're going to write out a little table here of all the possible things that we could possibly use in these equations. We could talk about the distance, delta x, the initial velocity, the final velocity, the acceleration, and the time. Okay. So with this, we're going to fill this in as much as possible. So the velocities were given, so we'll just throw those in. So 4.75 meters per second and 0 meters per second for initial final. We do not know the distance we went because that's what we want in the problem. So what we want, let's just give that a little star. We do not know the acceleration that is causing this motion from here to here. So we don't know the acceleration along this path. So that's an unknown. and the time it takes to go from initial to final is also not given. Now, the thing that you have to remember with these kinematic equations is that you always require knowing one particular thing unless you're solving for it, is you need to know the acceleration. In this problem, since we're not asked for the acceleration, then we definitely need the acceleration to get anything else. So the acceleration is going to be a vital thing to get before we can get this. We have to find another way to get it, because if we try to use in one of these equations to solve for the acceleration, we're not going to have enough information to solve this. There's too many things missing. So we have to go somewhere else. But we know that friction acts on them during the course of that trip from initial to final. We are given the coefficient of friction. So we ought to be talking about friction and the forces that are related to this problem. So we probably should draw the forces. Okay. Forces would include, so let me move this so I can do a free body diagram. So it has a mass, so it has a weight, so the weight points straight down, mg. It's on a surface, so they're in contact with the surface, they push into the surface pushes back, perpendicular, that's the normal force. Friction is opposite to the direction you tend to move. You're tending to move to the right, so the friction resists to the left. And in this problem, it is kinetic friction because you are sliding along it. Okay. Those are the forces that are acting on the object as it moves from initial to final. So when you do this kinematics problem, you have to realize, okay, so I am doing everything along the x-axis. The motion is along the x, okay? So when we solve for like the distance moved, it's the distance along the x. So you have to see that all these kinematic equations are in the x direction. So let's also just say this is like the x component of the acceleration to be specific. If we're talking about the x direction for the motion, and we're considering the forces, we should realize that we need to consider the forces only in the x direction. So in order to find the acceleration, so need acceleration first, we can relate the acceleration that we need before we can get this to the forces using Newton's law in the x direction. So sum of forces in the x equals mass times acceleration in the x. We do have an acceleration we're expecting, so we're going to leave that side alone, especially because we just want to solve for it. Left side, we're going to consider all forces that are acting on the object with an x component. It's only the friction in this problem, and it points in the negative x direction, given that the positive x direction is to the right. So I will write negative friction because it points to the left. The friction does have an equation that you can write out because we're not given the friction force, we're only given the coefficient. So we need to plug in the equation for friction, which is the coefficient times the normal force. That's still equal to the right side, which is mass times acceleration. Now, you still do not know what the normal force is equal to immediately, but because the normal force is in the y direction, we can solve for that using Newton's law in the y direction. So find normal force. Okay. So sum of forces in the y direction equals mass times acceleration in the y direction. There is no motion ever expected in the problem in the y direction, so we know the acceleration is 0 for that particular direction. Okay. So sum of forces in the y equals 0. The sum of all forces in the y, we have normal force up, that's positive, so we'll write positive n. And we have a weight downward, so minus mg. And there's no other y components of forces, just those two. In this particular problem, not in all problems, normal force equals the weight. Okay. Be careful of using the normal force as the weight. In some problems, it will not just be the weight, and this is how you will find what it is by doing the sum of forces in the direction that has the normal force in it. Since it's just the weight, we're going to just plug it back into here. Okay, so plug into x direction where we needed it. Plug that in. So going back here, we have minus coefficient of friction times the normal force, which we found it was mg in this particular problem, equals the right side, which is mass, times acceleration in the x. Two terms in total. We have mass in both terms, which means we can cancel it. So the mass drops out from both sides. It's not even given in the problem, so it shouldn't matter. The acceleration equals minus coefficient times g. So we're going to use this to get the acceleration. We can just calculate that now. Minus 0.775 for the coefficient times the gravitational acceleration, 9.8 meters per second squared. Plug that in. 0.775 times 9.8 is negative 7.595 meters per second squared. This is the value that needs to go into this table. So what we could do at this point is treat that as a given now, and let's solve this out given that we know the acceleration now. Before I erase anything off of the board, before I erase any of this, let me know if you have any questions so far up to this point, and otherwise give me a thumbs up and we'll move on from there and continue solving the problem. Any questions before we move on and I erase the left part of the board? Okay, got it. Okay, so let's erase the diagram and let's solve the rest of this problem. Okay, so for this, we have the acceleration. That's a given now. The only other thing we're missing in this table that's not the thing we're trying to find is the time. So what we're going to do is we're going to do our best to avoid using the time if we don't have to use it. You looking at the kinematic equations, there are ones that have time in it, which we're going to try to avoid. So we're going to use this middle one to solve for this distance, so we have the distance there, and we don't have to use the time in it, so we should be able to solve that. So we're going to use this one here, the second one. V final squared, just copying it down, equals V initial squared plus 2a delta x. We know that the final velocity is 0, so we can just get rid of that immediately. So 0 equals V initial squared plus 2a delta x. To get delta x by itself, the distance that we need in the problem, we need to move the initial velocity over. It's positive, so we're going to subtract it. So minus V initial squared equals 2a delta x. To get delta x by itself, we're going to just clean off the 2a by dividing it, because it's attached by multiplication. So minus V initial squared over 2a is delta x. At this point, you just check that you have everything. You do. And just plug it in. So we have that delta x equals negative. The negative is not part of the thing that's squared. It's only the initial velocity that's being squared. So we have 4.75 meters per second squared. Don't forget to square it. Divided by 2 times the acceleration, which is negative 7 0.595 meters per second squared. Okay. Units will cancel out because it's meters squared per second squared, and then here you're basically lacking one of the meters. So you'll cancel everything out except for meters, and you should get a distance in meters. So plugging that in. So we have that times 2 in the bottom, and then we have 4.75 squared in the top. So we get 1.49 meters. So that gives us our distance, and that's how far they slid before they came to rest. Okay. So again, it's just a kinematics problem. If you are allowed to use conservation of energy, you can use conservation of energy also to solve this problem, and you will have to account for the work done by friction in the problem. Okay. Let me know if there are any questions on anything left over, and let's call it about there for now, and we'll pick up tomorrow at 8 a.m. in the morning. So let me know if everything's good, or give me a thumbs up, and we'll go from there. Okay, I think it looks like we're good. So, yeah, so the plan is tomorrow, 8 a.m. So same exact time, and we're going to finish this up, and most likely we're going to emphasize doing chapters 8, 9, and 10, the most recent material. So that's what we'll cover tomorrow morning, likely, unless anyone says otherwise. Any last things before we end it for today? Okay, looks good. No problem, anytime. So yeah. Feel free to reach out and let me know if there's anything you want to focus on tomorrow. Otherwise, yeah. Thanks for joining in. And yeah, so I'll see you all tomorrow at 8 a.m. for the same live stream. We'll just continue on and do more stuff. This live stream will be posted very shortly after it processes, so you'll be able to replay the whole live stream and look at all the problems that we covered shortly. Should be up probably in the next hour or two that you'll get to replay this. So, all right. And then if you have any questions, then also my email is on my website. So just go to cloudsprinkle.com, and then you can contact me there if you need to as well. So thanks for tuning in.